Thanks, guys. Thank you all. Hello, yes, I'm a postdoc at University of Maryland in Goddard. And this series of talks in this section by me, Aparna, and Dave will mostly be about high-resolution imaging of microlensing targets after the microlensing events, basically. My title slide, a lot of the work that I do is with the Keck adaptive optics system, so the two telescopes on the summit of Mauna Kea, and using laser guide star adaptive optics, we can really improve the spatial resolution of Keck imaging. So this is a pretty well-known animation showing stars at the galactic center with adaptive optics off, and when you turn it on, you get extremely good spatial resolution. Okay, and this is a tech program I'll talk about that I've been working on with collaborators at UC San Diego, Kemming Zhang and Quinn Konopacki. Yes, so not everyone here is microlenser. I made this animation some years ago. It's pretty simplistic, but I like to show it just to motivate the reason why high resolution imaging is important for microlensing targets. So if we start with a real image, this one comes from Keck. This is a real image of crowded field of stars from Keck. And if we zoom in on just two stars, I'll call one the source and one the lens star. And now we're in simulation land, so it's not real data anymore. But many years before a microlensing event, of course, all the stars are moving. They have relative proper motions. And these source and lens, as well as our system, we move, of course. At 0 years, the alignment is such that microlensing occurs. And several years after the microlensing event, of course, the two stars continue moving on the plane of the sky. And so the main idea with high resolution imaging is we see a microlensing event somewhere, and then maybe it has a planetary signal or something. And then several years later, we point a big telescope at that target and try and directly measure flux coming from the lens system, the lens host, if it is a star. And this helps break some degeneracies in microlensing and helps basically give us a direct measurement or a very good understanding of the mass of the lens and its companion that's orbiting it. Okay, so this Keck program was conducted summer 2024, a few months ago. And the target list comes from the Koshimoto 2023 paper and Shemik's paper in 2024. I'll note Shemik-Mraz's paper is actually a Keck follow-up paper itself. So these targets in Shemik's paper were observed with Keck in 2021. These are the MOA 9-year FFP candidates that were discussed in the earlier sections. And I'm highlighting the targets that we observed with Keck in 2024, a few months ago. Most of them are from the MOA 9-year. There's one from the Shemik-Mraz study. I don't have enough time to go through our results, and we're not ready to present all of our results. So I'll just show a few examples. Before that, I wanted to explain some image quality metrics from Keck. This metric called the Strel ratio is used a lot, and as well as the full width half max, the size of the point spread function, is used a lot in adaptive optics imaging. So Strel, for anyone not familiar, basically it's this ratio between the real PSF intensity and going through the optical system compared to the perfect PSF. And so with no aberrations or anything. And so this value is typically between 0 and 1. So these are the 5 9-year targets that we observed, and the median Strel ratio in full width half max. And so the point here is that on the nights that we observed, 2 nights, the image quality was pretty consistent, pretty good across both nights. Not the best that we've ever done with Keck, but this is still pretty good. 60 milliarc second full width half max is quite good. Okay, I'll just talk about one of the MOA-II near targets right now, the terrestrial mass FFP. So from the talks earlier this morning, this is 5919, quite a low mass FFP candidate. So the Keck imaging was pretty good quality. And on the left is the target, the source, and a nearby unrelated neighbor, the source. And if I take and build a point spread function and build a PSF model and fit and subtract the source, I see a very clear signal in the residual. And so this shows kind of a dipole structure if you have two blended point sources and you fit one PSF model to it, you get this two lobes on the side and then a dark over subtraction in the middle. And if I fit two PSF models, I get a smoother residual. There's still a little bit of noise here and there, but a much smoother residual image. So this is kind of interesting because the idea, if 5919 is a true FFP, then, and the source is a single source, then we would expect to not see a dipole structure, which is indicative of two stars there. I don't want to make some people sad that maybe this is 5919 is a wide orbit bound planet. I'm not claiming that yet. But there are two objects here. They're separated by 18 milliarc seconds on the sky. The predicted lens source separation in this epoch of data from 2024 in Keck should be 90 milliarc seconds. So the separation of these two objects is much smaller than the lens source separation that's predicted. So the question is, what is the second object? One of them is the source. What's the second object? So there's a few possibilities. It could be a companion to the source. The source could be a binary. It could be the lens host, so a host star for this 5919 planet, where the mu rel vector, so the relative proper motion direction, is aligned more or less with the planet and star separation. So you could imagine maybe the FFP signal occurred, so this planet caused the lensing signal, and then maybe their motion, the host, if it is a host star of this planet, trailed behind the planet's signal, and maybe that's what I'm detecting here is maybe the host that's much closer to the source at this point in time. If that in that scenario, there may or may not be another potential signal from the primary host star later in the baseline. So more work needs to be done. I don't know the answer to this yet, but maybe having some conversations or looking back at some of this baseline to see if there's any subtle signature, and maybe can, based on the separation of this second star, see in time where the signal might be. But it also very well doesn't have to be any signal from the host star at all. So it's still up in the air. There's not a firm answer yet, but there is definitely two objects that are very close to each other on this target. That's all on 5919. I'll speak briefly on OGLE 2012-1072. That's the target from Shemek-Maratz's paper in 2024. So I looked at the original data. I re-reduced some of the Keck data in 2021. And for this target, I saw something that looked kind of interesting in the image, but it's also kind of noisy. So this, again, I'm bringing back up this Strel and full width half max plot. These are the older, the other MOA-II near targets, very faint right here. So I'm only focusing on the new Keck data that we got on this target, and the Maratz 2024 data that was obtained in 2021. So the new data is significantly higher image quality, smaller full width half max, better image quality generally. So first, I'm going to show the Keck imaging from 2021. The source star is in the middle here. It's pretty noisy, but I re-reduce the data and I subtract all the stars. I fit all the stars and I subtract them again. And I don't know if can anyone point out, it's pretty noisy, but there's potentially something that might be in this region around where the bright source was subtracted, but it's also quite noisy. So it's nothing definitive, I would say, in the form of a potential host star for this FFP candidate. That is re-reducing the 2021 data. So we did also get 2024 data, which is not this yet. This is just showing again the original data. So the subtracted image I just showed, and these panels come from Shemik's paper in 2024. So star 1 is the host. And I'll note that he did detect another star, which he calls star 5, which has a separation that's much too large to be the host. And then the residual here. And maybe where I found a residual in my re-reduction, there might still be something here in this, but that is the original. So there's star 1 and star 5 from Shemik's paper earlier this year. So new Keck AO imaging is much higher quality. Here's the source. And this is a few years later, after 2021, when the first epoch of data was. And here is a residual. So I'm going to show a lot of these residuals, but so I fit all the stars with the PSF model and subtract. And I see star number 5 that Shemik identified in the 2024 paper here. And this signal seems to still be there in the new 2024 data. So that's a stronger belief that what might have been noise in the 2021 data is a real signal of another star here. So if I fit a PSF model to this star number 5 that Shemik identified, and I subtract that, I get this residual down here, still has somewhat of a signal. It's kind of noisy also. Then I fit a third PSF model to this signal, and I get generally a more or less smooth residual. There's still noise. There's still a question. I've gotten a question about, am I just fitting PSF models to noise and then fitting another PSF model to noise? That is a fair question. This signal in particular is here in 2 different epochs, in 2 imaging systems, NERP2 on Keck and OSIRIS on Keck. So it's pretty believable that that is a true signal. It's not just systematics or noise in one epoch or the other. The final verdict on this is it the true lens host star? I'm not sure. It seems like maybe it's not, and the reason why it's not, if I go back to the 2021 data, I fit the source star, I subtract it, I fit a PSF to this new candidate signal. The separation I measure between these is 66 plus or minus 10 milliarc seconds. That's pretty large error bar, like 15% or something on that separation, but it is what I measure in the 2021 data. In the 2024 data, the separation is measured to be lower. So between 2021 and 2024, it appears like the source and this new faint signal are getting closer or have less separation. So that, of course, means that it's very unlikely to be the host of this microlensing event. Otherwise, they'd be separating from each other. They'd be getting larger separation between the years. This is pretty good error bars. So it depends on who you ask, how you interpret this. This could be definitively ruling out this new signal as the potential host to this FFP candidate. The error bars are quite large. I would like to get at least one more pretty high quality epoch, just to confirm with smaller error bars that this signal is actually getting smaller in separation from the source. And I'll note our Keck program did get awarded 4 half nights next year in 2025. So whether or not that separation between 2024 and 2025 is enough to measure what that is a question. But with that, that's my last slide. And I don't have any conclusions because there are none yet. We're still analyzing a lot of the data, but happy to take any questions. Thanks.
Yeah, so I wanted to make a comment about, you know, you measure these potential stars at some separation, but of course, we're looking for wide separation hosts. And so, you know, if the separation is really wide, then maybe that host will be still approaching many years afterwards if the elongation is, I mean, you know, if there's alignment between the separation and the proper motion. But in the case where you have, you know, a measurement of the relative proper motion from the light curve, like when you have finite source effects, then there's a more definitive test that, you know, the wide separation planets should have very low velocities which affect their hosts. And so you can just measure the velocity of the candidate host in 2 epochs. And, you know, if that's not consistent with, you know, the determination from the light curve, then that's more definitively ruling out instead of, you know, ruling it out to 99.5% probability, but this, you know, possible misalignment. Alignment.
Yes. Multiple Keck high resolution epochs are great for many reasons.
But also when you have that measurement of relative proper motion.
Also from the light curve, you need a mu-rel estimate, decently constrained.
Hi, how did you build your PSF model to subtract out the primary star PSF?
Yeah, good question. So I wrote a software as part of my PhD thesis that takes from the Keck images, from a stack, basically all the exposures stacked together. It picks, so I select by hand, basically real stars that are near the target in the Keck image, that stars that appear to be well behaved, they appear to be single, decently well characterized stars, and that PSF is averaged together in a DAO font software to build the empirical PSF model. Yeah.
Okay, so it's empirically built with simultaneous PSFs.
Yes.
Great. And then, did you make a contrast curve where you inject and try to recover close sources?
I've done that for other targets, not any of these FFPs yet, but that's on the to-do list, definitely. Yep.
Thank you.
Awesome talk. So I had 2 questions for you. One was when you're talking about MOA-II 5919, you had said, okay, maybe actually it could be a widebound thing. You know, you don't want to rule out anything yet, but it could be widebound. Is this the extremely short duration one? This is sort of the lowest.
Yeah.
Okay.
If it did have a host and it's a wide orbit planet, that's arguably more exotic and more unique than if it's the FFP, because it would be in that, I think Shemek showed that in that parameter space, that's a very, very low mass, very low mass thing at a very, very wide orbit is,
yeah. So I was wondering about that. And I was also wondering, sort of to the point that Sean had asked earlier about the fit to the FFPs, you know, if reinterpreting this as a just very wide binary actually says something interesting either about the binary population or sorry, not binary, but bound. Or the FFP thing. Okay, cool. The other thing was a crazier question, which was, given that your sort of nominal extra star is moving towards the source right now, will it lens the source at some point? Can you predict when?
Very likely not. So these measurements are made in a relative frame. So there's the relative separation and the relative proper motion between the lens and the source. So Yeah, the absolute, you know, the magnitude of that separation can be getting smaller, but it doesn't mean that they're perfectly moving, you know, toward each other to overlap. So I do have multiple epics, so I could use something like Gaia DR3 and get a absolute reference frame and then maybe check, which might be useful, but not just from this relative measurement. No.
Okay,
Yeah.
I mean, that would be,
Yeah.
if you could predict that, that would be super cool.
Yeah.
And